Okay, we've got a minute or so to start, but I'll go ahead and get the recording started since a lot of students are here. Um, I will put out the correct link. Apologies, the link I gave to the Hailstone file on Monday night had an extra home in it. I posted the correct link on Slack. I also put that file on GitHub and Blackboard, and I'll give you the correct link in a minute. And then hopefully we can actually teach recursion and correct from that holy mess of a lecture on Monday when I rush through, but we'll try to explain what's going on. My clock says 4 o'clock, so we will get started. Today is more on recursion and hopefully, as I said, some more details and make it a little bit clearer what we're trying to do. I'm sorry, if someone is saying something, you were breaking up. Could you repeat? Okay. I will go ahead then and go back to administrative notes. This is the correct location of the file that you copy. The path I gave you the other day had an extraneous home in it after my name. And that led you to a directory that I actually can't give privileges to share. So this is the correct public file. And as I mentioned, I put the actual file itself on GitHub and on Blackboard as well. So hopefully from one of the three, you can get that file to fill in. Remember that lecture lab is due tomorrow night. Project 2, getting some good questions. If you have questions, keep them coming. Remember, it's not due till next Friday, till Monday the following, not next Monday, but following Monday the 27th. But the earlier you get into it, the better off you're going to be. And also for those who have not seen, all 201 sections got the common final period. The schedule is out and our final exam is set to be 1 month from today, Friday night, the 15th of May from 6 to 8 p.m. The joke is that the reservoir believes that anybody taking computer science classes has nothing else to do on Friday nights anyway. So for some reason, every semester we get the 6 to 8 p.m. Friday final. My current plan is that we will have the test on Blackboard at that time, similar to the way we did exam 2. That wasn't great, but it seemed to be okay. If anything changes, I'll keep you posted. You know, we got lots of stuff before then. But for now, plan on Friday the 15th of May, 6 to 8 p.m. being online to take the exam on Blackboard. And of course, if that's going to be a problem for you, let me know and we'll take care of. All right. So Monday, I showed you a recursive program that calculated a factorial, and I showed you a visualization. But let's be serious, that was not the best lecture I've ever given. I mean, what the heck were we visualizing anyway? If you recall, we were on this Python tutor site, sorry, wrong link, with this program, factorial function with a main program that consisted of one line that called it. And then as I ran through it, it went through and created new frames. Okay. Not exactly clear, not exactly intuitive. What I want to do now is stop, slow down a little bit, and try to explain clearly what exactly we were doing. Here we're going to get into some more computer science, and I'm going to elaborate on some things I taught earlier in the semester. Okay. Python, like many, but not all programming languages, executes by using a stack of frames to keep track of where it is in the program. Now I got two undefined terms, stack and frames. So let's go through this and see if we can explain. This stack and frames on the stack keep track of what instruction is being executed now, what instruction gets executed next. It's where the symbol table I talked about a couple of times in this class is. It tells you what variables are in scope, what can be used now, and what can be accessed, and where they are in memory. And it also tells you, if we're in a function, where do we go when this function finishes? So that's how Python keeps control. The way Python keeps control of where it is and what's going on is by having a stack, and on this stack are a set of frames. It determines exactly how the program's working. And I'm going to make a statement that I'm going to explain. Only the frame on top of the stack can be executed. That's really important. Let's go through that. What do I mean again? I haven't defined these two terms, a stack and frames. A stack is a data structure. In computer science, you talk about things in terms of either data or algorithms. An algorithm is your program. It's what you do. It's the set of steps you take. A data structure is just a way of organizing data that has a defined set of rules about what can be done. A list is a data structure. A dictionary is a data structure. Well, a stack is something similar to a list or a dictionary, but it has different operations. The only thing you can do with a stack is you can put something on top of it, which is called push, or you can take something off of it, which is called pop. You can literally think of this as a stack of papers. You know, if you're sitting in there, the old-fashioned dead tree version, you get something and you put it on top, and the only paper you can work on is the thing that's on top. Now we're going to try another visualization, another illustration, and hope it makes more sense than the other ones. This is something where I have nothing. Okay. And what I'm going to do is I'm going to take the number 3 and I'm going to push it. And the number 3 gets added to my stack. See if I can make this a little bigger. Now I'm going to take the number 4 and I'm going to put that on my stack. And now number 4, it's to the right, so it's a little confusing, but this is the top of the stack is to the right. I've added an element to the stack, and that's called 4. Okay, now I add 9, and that gets pushed onto the stack. The only thing I can deal with in this stack is the element on the top, and that's this element 9. When I'm done with 9, I can remove it from the stack by popping it. It's gone. Now I can deal with 4. That's the concept. Hopefully in a minute it'll make more sense. Okay. Now, so I just sort of explained stack. Now, the other word I had not defined a minute ago is the frame. In Python and in some other languages, but in Python, a frame is the set of all the symbols currently in scope, currently known to the Python interpreter. That's all my local variables. That's all my constants. That's my function names that are known. That's my parameters. That's global variables that I'm not supposed to use if you know. That is known as the frame. It's the set of all symbols known to the Python interpreter. When the program starts, it pushes the main program's frame onto the stack, and now we're executing. So we start executing when the main program's frame is pushed onto the stack, and now the main program starts executing. Whenever we call a function, not when we define a function, the definitions don't count, they're just things we write down. When we call a function, Python creates a new frame for that function and pushes that frame onto the stack. Since that function's frame's on top of the stack, that function is now executing. Now let me go back to this visualization to see if this helps. Okay. I create the main program. Well, hang on a second. Let me pop the older two values out so I can start. I create a main program. The main program gets pushed onto the programming stack, and now the main program is executing. I am working in this code with this memory, and this is what I know about. Now, in that factorial example, I called factorial with an argument of 5. So let's just, this limits me to 4 characters. So let's call this, the function factorial is denoted as f, and I called f with an argument of 5. So when that call is made, remember what I just said on the slide. When that call is made, Python is going to create a new frame and it's going to push it onto the stack. So right now I created factorial of 5, and now I'm going to push it onto the stack. This is my execution stack in the computer, and this is what Python is executing. And this factorial of 5 is on top of the stack, and that is where we're executing right now. Now, if you look at the code for factorial, I'm not going to hop back for fear of losing people, but if you remember the code for factorial, it checks to see the base case. Is the parameter 1? In this case, the parameter is not 1, it's 5. So we go down to the next one and we say return 5 times factorial of 4. Now, recursive call. We have to make another call to factorial, and this time an argument 4. And now Python creates another frame for factorial of 4, and it pushes it onto the stack. Python is now, I'm sorry, I see someone is trying to speak, but I'm not hearing. Can you try again, Daniela?
Oh, I'm not trying to speak. I'm on my phone. I'm sorry.
Oh, no problem at all. I've decided to use the WebEx options where it tells me when someone's trying to speak, and it popped up that you were. Don't worry about it. Not a problem. Okay.
Sorry.
Getting back to this. Now, Python has pushed the frame for factorial with the argument of 4 onto the stack. That's what's on the top. It's on the right. Just bear with me. Python is executing in the frame of factorial 4. You'll notice we have factorial with 5 still on the stack. We have the main program still on the stack. We can't execute those. We can only execute in the frame where that's currently on top of the stack. So we can only execute with factorial 4. Okay, so let's execute.
Question.
Go right ahead.
So essentially, the function factorial 4 is running inside of factorial 5, correct?
It's running on top of is the term we like to use.
Okay.
Inside has another connotation that I don't want to get into, but we use the term on top of. Okay, great question though. Great question. Now, factorial 4, the first thing we do is check to see is the parameter 1. It's not, it's 4. So we go down to in the else statement and we say call factorial n times, and now factorial of 3. So Python has to create another frame, and it pushes that frame on top of the stack. Now you can see the stack is starting to get pretty big. It's got main, it's got factorial of 5, it's got factorial of 4, it's got factorial of 3. But the only way it can execute is factorial of 3. Okay, factorial of 3 works the same as the others. Is the parameter equal 1? No. So therefore, call factorial of 2. That gets pushed onto the frame. That frame gets pushed onto the stack. Factorial of 2. 2 is not 1. Call it again. Now we push factorial of 1 onto the stack. So here we have a stack that's got 6 different frames on it. Okay. We've got the main, we've got factorial of 5, we've got factorial of 4, we've got 3, 2, 1. All of these other versions, all of these other clones of factorial, right? They're hanging around waiting for a value. They can't execute. They're not on the top of the stack. They can't execute. They're hanging around waiting. The code and variables are all known. They're there in the computer, but they can't do anything. They have to wait for a return. Now, factorial of 1 says if this equals 1, parameter equals 1, then return 1. Yes, indeed. Factorial, the parameter is 1. So now we return 1. Now, when the function ends, and we'll talk about that, but it ends when you hit a return statement. When that function ends, now we return the value of 1 and we pop that value off the stack. We no longer need factorial of 1 is done. So that frame is popped off the stack. Now Python in control says, oh, what's on top of the stack? What's on top of the stack is this frame with the parameter of 2. Well, now I got a value of 1 returned. And so now I finish that statement that says I return 2 times the 1. Now I can return 2. Aha, I've just executed a return statement, return 2. When I execute a return statement, that function stops and I can pop it off the stack. Now what's on top of the stack is factorial with 3. It got a returned value of 2. And now it can say, okay, it can continue to go again. It says, okay, multiply 3 times what was returned. What was returned is 2. That means I need to return 6, 3 times 2. Pop that off the stack. Now what's on top of the stack is factorial of 4. Okay, now I can resume because I'm on top. I got a value of 6 returned to me. I say return 4 times that return value of 6, that's 24. Okay, I'm going to return 24. And now that I've executed that return statement, it's gone. Now control passes to factorial of 5. Okay, I got the value of 24 returned to me. Multiply 5 times that value, 24 is 100. 5 times 24 is 120. I return 120. Now I can pop that off the stack. Now I'm back in the main program. The main program, which had factorial of 5, got returned a value of 120. So now the main program can do whatever it does. Okay. Well, there's no other code in the main program. The main program just consisted of a call to factorial with 5. So the main program is now done. Now I can pop that off. This is done. And now when everything is done, when everything is popped off, now I know that I'm done. Okay, so that hopefully is a little bit clearer, and we'll walk through a couple more things. When the main program called the function, when it called factorial, Python created a new frame and pushed that onto the stack. And that function is what's being executed because it's on top of the stack. And that's why it's important that this as a data structure is a stack. And the only role of the stack is you can push and pop. You can only deal with what's on top. What's lower in the stack, you can't do anything with.
Can I ask a question?
Certainly.
What you're saying makes sense, but then I just don't understand why, I guess, what I have doesn't go in a loop. Like the function we have doesn't go in a loop because you said that if n equals 1, we should return 1. But if it equals like I guess anything else other than 1, it's basically n times n minus 1 factorial. But like so example, if we had the 6, it would go to like 6 times factorial 5 factor, and it keeps going until it gets to 1. And then at 1 it returns 1 inside the function. But then still there isn't like I guess like any function that tells the factorial inside the factorial like how to solve itself.
Okay, that's a great question. And the answer to your question is yes, you could do it that way. And just a second, I'm going to find the right slide. Okay, this slide, which we talked about on Monday, is exactly what you said. Okay, on the left side of the slide where it says iterative is exactly how you would do this in a loop. So you could. You are exactly correct. We could do this in a loop, for loop, while loop, whichever, and it would work perfect. But what we've said is sometimes, now maybe not with this example, maybe with some examples we'll talk about. Sometimes it is easier to talk about how to solve the problem recursively with these pushes and pops than it is to do it in a loop. Okay, so we have both tools in our toolkit. We can do it with loops. You are exactly correct. We could have done this in a loop and never needed to do recursion. But we also have recursion to do the same problem.
But
That's the point. Okay?
yeah, but I'm saying like inside the second like in the recursive function, inside the second return statement,
Yes.
it would be n times factorial of 5 times factorial of 4 times factorial. Like, how does the factorial know that it's changing to like a number, like after it goes through the loop again?
Okay. When this return statement, when the function ends, it passes back its value in the return. So what happens is factorial 2 gets replaced by the value 2 when that function ends, when that return is executed. Only when that function ends does that value get passed.
Okay, so it passes back the value that's given.
Right, it passes back the value that's given.
Is it because of our base case, or is it just our recursive? Is that just our recursive statement for?
Yeah, actually, the way recursion works, nothing gets passed back until we get to the base case.
Okay.
So when we said factorial 3, we didn't get 2 passed back or 6 passed back right away, right? Nothing got passed back until we executed it all the way down to the base case.
Okay.
And only then did things start getting passed back.
All right. Thank you.
Keep these questions coming. This is a strange topic, and we need to make sure it's understood. Okay. So getting back to this, when the function ends, the frame is popped off the stack, we pass the return value. Now, when we pop that frame off the stack, it means remove the top element from the stack. All of its parameters, all of its local variables disappear. We no longer have access to them. We only have access to the value that was passed back in the return statement. Okay. And so program control returns to whatever frame is now on top of the stack. That is whatever called that function. Now we're back executing there. So when factorial of 1 ended, now we can execute for factorial of 2. Not until. We can't do factorial of 3, 4, etc. until those frames end. So we can only do one thing at a time. Something we have covered, but I'll go over again. When does a function end? Remember, the frame doesn't get popped off until the function ends. The function ends either when a return statement is executed. When a return statement is executed, nothing else happens in that function. At that point, immediately, the function stops, the frame is popped off the stack, the return values are returned, and we're done. And the other case is we can be lazy. We don't have to include a return statement. If we don't include a return statement, what is returned is the value none. But that's when all the code in the function has been executed. When all the code in the function has been executed, the function ends even if there's no return statement. That's the same as having a return statement that says return none. So when a return statement is executed right there, doesn't matter, you still got code, you're done. If there is no return statement, then you execute all the code and then you're done. That's when the function ends, and that's when his frame can be popped off the stack. When does the whole thing end? When all the main program's code has been executed. Okay. In our example, when factorial 5 was executed, since that was the only thing in the main program, when all the main program's code has been executed, the main program's frame is popped off the stack, and that's the end of it. Since there's no place to return control to after the main program is done, that's when the program is over. So the program ends when the main program's frame is popped off the stack because there's no place else to return control. You're done. Now, again, this assumes there were no errors. If there were errors that crashed your program, then, there's some inside garbage keeping, garbage cleaning, garbage collection is what it's called, and cleaning that happens inside the program that we don't worry about. Your program's over, it's dead. Everything cleaned up after it. But assuming there were no errors and assuming your program ended the way you wanted it to, it ends when the main program has been executed.
Quick question.
Sure.
So basically, for a function to be recursive, you basically need at least 2 return statements, correct?
You should, yes. I'm going to say yes. Somebody could probably provide me a truly strange example without it, but I'm going to say yes.
You need one to return the final value and one to recurse itself.
That's correct. You need a return for the base case and you need a return for the recursive case.
Okay, great.
You should have 2. Like I said, somebody could probably show me something totally, completely strange that I wouldn't understand that did it without it, but for now, yes. Okay. So now this is something I rushed through on Monday, but I want to go through it a little more slowly now that we have time. So the Fibonacci sequence of numbers is another one that's good to represent in recursive programming. The Fibonacci sequence from math and a number of other fields, you start with 1 and 1. And from then on, every number is the sum of the 2 previous numbers. So 1 and 1 is 2, the next number is 2. 1 and 2 is 3, the next number is 3. 2 and 3 is 5, the next number is 5, and so on, 8, 13. So we can express the Fibonacci sequence as the nth number, any number, the nth number is just equal to the nth Fibonacci number is the n minus first Fibonacci number plus the n minus second Fibonacci number. Now, we can talk about this iteratively, but you can see the iterative solution in this one is actually kind of a pain because you have this for loop buried inside an if else because you have to handle a small number. I mean, the iterative solution works. That code works. It gives you the right value. But it's actually a little bit cleaner to do it recursively. Here is your base case. Sorry, I can't highlight in presentation mode. Your base case is, all right. Here we go. Your base case is if n is less than 3, if n is 1 or n is 2. The first Fibonacci number is 1. The second Fibonacci number is 2. I could have written this as n less than or equal to 2. That's fine. I chose to do it if n less than 3. I'm just going to return 1 because the first Fibonacci number is 1. The second Fibonacci number is 1. If you give me 0 for n, the 0th number is undefined. I'm going to throw you an error. I'm not going to worry about it right now. Okay? So you give me a positive integer. If you give me 1 or 2, I just return 1, and that is my base case. If you give me any number greater than or equal to 3, I'm just going to calculate recursively the n minus first number and the n minus second number. So basically, I'm going to calculate all the numbers. If you ask me for the 21st number, then I would have to calculate all of them. So let's, at the moment, go to PyCharm, and let me go back and share PyCharm in just a second. Here we go. And we'll put a main program, print fib of 21. Now, hopefully I haven't made a typing error and this will work. This shows me that the 21st Fibonacci number is 10,946. Okay. If I go through this code and I wanted to see it in action, what I would do is put in a print statement and I'm just going to print the n minus first Fibonacci number. And this is actually probably going to take some time because you'll notice I'm calling recursion. Let me change this just a bit. Let's do this. X equals fib of n minus 1. That's one recursive case. Y equals fib of n minus 2. Now I'm going to print X is X and Y is Y. And I'm just going to return X plus Y. This saves me from having to recurse twice and really killing time. Now let's make sure this works. The point of all this, presuming it works, is to show you that we're getting intermediate steps. Okay, and you can see now that we've calculated all the Fibonacci numbers. Okay, and we started here with X and Y, 1 and 1, 2, 3 and 2, 8 and 5, 21 and 13. I'm not printing out all of them because of the way this recursion is working, but you can see what I'm doing. I'm calculating the 20th to get the 21st. I'm calculating the 20th and I'm calculating the 19th. Okay. And this is actually how I calculate the 19th. This whole sequence of things is calculating the 19th. The previous sequence is calculating the 20th. And so that's a bunch of extra code, extra printing, but that shows you recursively that I go through and calculate each one. And if I scroll up, you'll see that it went through all of those loops a number of times. But this is just an illustration of how you do recursion, specifically with the Fibonacci sequence, to calculate. Now, let me see if I can get the screen back to normal size and go into presentation mode. Okay. So that was just another illustration that I didn't get, another example that I didn't really get through on Monday, but it's in Monday's slides. I wanted to cover it. We're not going to bother tracing that one again. It does the same thing. But you can see it yourself by following that link. All right. So I assign you, now if you're paying attention to what's going on with the major sections, I chose to give you the exam on the scheduled date and not put recursion on exam 2. What the majors are doing is they're taking their test this week because Johnson and Hamilton chose to put recursion on this test. So if you talk to any of the comp sci majors taking 201, they've got recursion on their exam. So there's lots of stuff about how to solve a problem using recursion. Now, you're not allowed to give them any answers, but this is what they're tearing their hair about. How do you solve a problem using recursion? And the first thing you have to ask yourself, the first thing you have to answer before you decide that you can solve a problem recursively is you have to identify the base case. Now, there may be more than one. There may be more than one. In the Fibonacci case, there actually were 2 base cases. What if n is 1 and what if n is 2? I combined them into one by saying n less than 3 because I did the same thing in each case, right? But I could identify in the Fibonacci sequence the base case. Now, remember what I said on Monday, and let's try to make this clearer. Recursion only works if the recursive case is a simpler version of the problem or a subproblem of the problem. Okay, I can calculate factorial 5 recursively because I can calculate factorial 4 a little easier. And and 3 is easier than 4. I can make the problem simpler. If I tried to do factorial 5 by calculating factorial 5, it's not going to work. I'm in an infinite loop. My subproblem is not easier. So I have to figure out the base case, and then I have to figure out a simpler version of my problem to be the recursive case. And I have to convince myself that if I keep applying that same recursive case over and over, eventually I'm going to get to a base case. So with factorial, I'm going to say, well, the base case is 1 factorial. 1 factorial is just 1. We're done, yay. I then have to convince myself that by saying my recursive case is factorial of n minus 1, it's simpler. 5, 4 is simpler, 3 is simpler. I have to convince myself that if I keep applying that recursive case, I'm eventually going to get to a base case. If I'm not, throw recursion out the door, it doesn't work. So we have to trust that the recursive calls work, and we have to convince ourselves that if the recursive calls work correctly, I'm going to get to a base case. Now, if I have a base case and I have a recursive case, do I really solve my problem? If my base case plus my recursive case don't solve my original problem, then they're useless. I haven't got an answer to my problem. So before you sit down and say, I can do this recursively, you have to convince yourself, I have a base case and I have a recursive case that is a solution to my problem. Now we're going to go through some examples to this. Okay. Here, and we'll walk through some coding, and I'll put the coding up on GitHub later on. It's not there now. I want to figure out whether a string is a palindrome. Palindrome is something that's the same forwards or backwards, throwing out white space. We don't care where word boundaries are. I want to do this recursively. Okay, we've done it iteratively. I want to do it recursively. Let's think about a base case. Here is, to me, a good base case. A string that is 1 character long is a palindrome. That seems like a good definition. I mean, the letter A. Forwards or backwards, the letter A is the letter A. There's no way around that. Any string that's 1 character long is a palindrome. Okay. That seems like a good base case. Is there another base case? Well, a string where the first character, is different from the last character is not a palindrome. All I have to do is check the first character and the last character. Anything that says CAT, the first character is not the same as the last character, that cannot possibly be a palindrome. So now I have 2 different base cases. One where it is a palindrome, a string that is 1 character, and the second where the first character is different from the last character, is not a palindrome, and that also helps solve the case where I have exactly 2 letters. If I have a string that's 2 letters, IS cannot be a palindrome. First character is different from last. So those are my base cases. I'm going to add 1 more base case. Well, let me come back and add that 1 more base case. What is a recursive case? A recursive case seems like this. We know that if the first character is different from the last character, it's not a palindrome, we're done. If the first character the same as the last character. The string is a palindrome if what's left when you throw away the first and last characters is a palindrome. Let me explain that. Give an example. Insert a blank slide. The string is yay. Ignore capitalization. I'll go back and fix it. The first character equals the last character. Now, create the substring by throwing away the first and last character. Take off the first Y, take off the last Y. Okay? We know how to do that. Okay? We can use string slicing. We know to start with a substring of, if the string here is called X, is our variable name that has the value yay, then we know that if we take X, start from 1, and go through the last character that we want, this Y is -1. So if we go through -1, or if you'd like, sub 1 length of X -1. If that makes it clearer, that's fine. Those are equivalent statements. Those are the same in Python. Let's make that a small x so we're confusing. If we do that, this is exactly the substring we're talking about. This gives you everything left other than the first and last characters. We've thrown away the first and last characters. So now we have what's left is A. Threw away the Y, threw away the Y. Now we have left is A. Well, we said before that a one-character string is by definition a palindrome. So now we can conclude that since the first character equals the last character, if the substring is a palindrome, the substring left is a palindrome, then this is a palindrome. So we can conclude recursively that this is a palindrome. And obviously, looking at it, we can say, yeah, it is. So the recursive case was to throw away the first and last characters if they're the same. And if what's left is a palindrome, then this is a palindrome. We made a simpler problem by having a simpler string, and we've called it recursively, and we've gotten down to a base case. Now, I mentioned there's one more base case that we have to cover, and now I'm going to explain it. Suppose I start with the string TT. It's a string 2 letters long. The first character is the last character. Now, suppose we create the substring and we throw away the first and last character. We have nothing left. Or alternatively, we have an empty string left. What do? We don't have an answer yet. So the base case that we have that we're going to have to address is a string that is 0 characters long, an empty string. We're going to say it is a palindrome because it gives us the right answer. Okay. This should certainly be a palindrome. I mean, that is spelled the same way forwards and backwards. So this should be a palindrome. So our rules should solve a problem. Remember, recursion, if we apply a base case and we apply a recursive case and put them together, we get the wrong answer for our problem, then we've done it wrong. Okay, we don't have the right answer. So that's why in this case with the palindrome, we had to add a base case. A string that's 0 characters long or 1 character long is a palindrome. So let's go in here and go in cold, which means you're going to get to watch me make lots of mistakes. I'm going to try to write the Fibonacci recursive code. So first, I'm going to define a function that gives me an answer, yes or no. Is this a palindrome? Function is underscore palindrome. It's going to take one parameter. That's going to be a string, which we'll call S. Now, we need our base cases. Okay, our base cases say a 0 or 1 character long string by definition is a palindrome. So I'm going to just write that as if length of S is less than 2. I'll put a space there to make it clearer. We return the Boolean value true. Okay, so I combine my two base cases, a 0 length string and a length of string 1, into a single if statement that says if the length is less than 2, then I'm going to return true. Else, now I have to deal with my other base case. What if the first character of this string is not the same as the last character of the string? Now, when I get to this else, remember, I've already verified we're going to assume that S is a string that's some integer number long, some number of characters long, right? We can't have a -3 length string. We can't have a 0 length string. It wouldn't, 0 is addressed. When we get to here, we already know there are at least 2 characters in this string. So it is perfectly correct for me to say, I'm going to change this to an elif. S, first character, that's 0, sorry, almost made an error. If S0 is not equal, I'm sorry, question?
Don't you need to have a prompt for the elif, like the condition?
Yes, you are correct. This, yeah. And you're right. That's a good point. I'm going to rewrite this. Instead, you get to watch me, foul up. Here is how to write this. Elif S sub 0 is not equal to S sub -1, the last character. So this is just checking to see if the first character and the last character are correct, are equal. If they're not equal, I'm going to return false. This is my last base case. So thank you for pointing that out. Yes, this is the correct way to write it. Saves time debugging, reading error messages. Okay, now I've taken care of all 3 of my base cases. 2 of them with this statement. The third base case is taken care of with this statement. Now I have to handle the recursive case. Else, I'm going to return is palindrome. And let's see if I can do this correctly. I'm going to chop off the first letter of my string, and I'm going to chop off the last letter of my string. So that should be a completely working function. And now I'm going to write a main program that's going to test, and hopefully I can spell this. Let's see if I can come up with a decent palindrome. Level. Level is a palindrome. Okay. So now I will go up to here and I will just tell PyCharm to run April 15, and April 15 worked, and the problem didn't have any bugs in it. The problem is I didn't do any printout. So let's go back to the Python console and do it there. Somebody asked, by the way, why I don't just run the code always using the PyCharm run statement. The answer is because a lot of times I'm mixing different programs in the same code file. And so if I tried to run it all at once, it wouldn't work right because I'd have multiple different main programs and multiple different functions. And so this is why I usually do this. So let's run this. And it tells me true. And now let's try with a different word that's not a palindrome. And it tells me false. Retriever is not a palindrome. Now, what I want to do, though, for curiosity's sake, is I want to print out where, in determining whether retriever was a palindrome, I want to print out where it failed. So what I'm going to do back is go back up to this base case. And before I return false, if S0 is not equal to S1, I'm going to print S sub 0, comma, is not equal to, comma, S sub negative 1. And now when I run that, if I haven't fouled something up, it's going to tell me where the palindrome algorithm failed. It helps if you try it with the right word. Let's change it to retriever. Here we go. And it tells me that it's failed on the T and the V. And if we look at this logically, we can see that this R is equal to that R, so it passed. This E, it then tried this substring, the E to E, and we see that this E is indeed equal to this E, so it passed. And then it tried on this substring, the T to V. And now we can see that the T is not equal to the V, and that's where it failed. And that's what it told us here. So in determining whether this function is a palindrome, recursively, we just checked our base cases. Is the length less than 2? If it is, return true. 2 base cases covered. Otherwise, if the first letter is not equal to the last letter, base case, return false. The answer is no. Otherwise, recursive case, chop the first letter and last letter off the string and recursively call the function and try that one. And we've shown that this works. And yes, I will post this code on GitHub later on tonight. Okay, so this is following our
Question.
Yep, go right ahead.
So you mentioned, well, actually, no, is there a way to think if given like a problem, if it's more beneficial to solve it recursively than with a loop?
What this comes down to is what makes more sense to you. and for now, and in your programming career ahead, the answer to that question is, if it makes more sense to you to solve it recursively, do that. And if it doesn't make sense to do recursively, go with a loop. And the reason I say that is two reasons. One, we said last time that you can always solve it with a loop. If you can solve it recursively, you can do it with a loop. Always, that's a fact. Okay. And the second thing is that in terms of how fast the program runs, consuming internal resources, how much memory, processor speed, etc., a loop is always going to run faster internally to the computer than recursion. So now these days, with clouds, with high-speed chips, with multi-cores, with terabytes of memory, we tend not to care about that. We tend not to care about iterative being faster than recursive. It comes down to what makes more sense to you. But you always can do it iteratively, and iteratively will run faster internally to the computer. So if it makes sense to you to do it recursively, do it recursively. If it does not make more sense, then throw recursion away and do it iteratively. So you get to exercise good judgment. Okay. All right. So the last slide I have are things that can be easily solved using recursion. We'll work through a couple of them. So we have 15, 20, almost 20 minutes left. We'll work through each for a couple of minutes, and then you can either go earlier or I'll answer questions if you have them, like on the lab or the program or whatever. Okay. Given x and y, calculate x to the y. Now, iteratively, that's fairly simple, right? If I wanted to do this iteratively, let me see if I can come up here. There we go. Okay. I'll insert a text box. Iterative solution to x to the y is for I in range of y. I need an initial, x equals 1. For x in range y. This wrong one. Y prod equals prod times x. That is the iterative solution to this problem. Okay, and there's nothing says you can't do that. That works fine. But we want to do it recursively. Okay, so doing it recursively, our base case is fairly simple. I've got two of them. I can pick either one. If I'm worried about somebody making y negative or 0 or whatever, then I've got to deal with it. But I'm going to say that my base case is x to the first power is equal to x. That's my base case. If somebody gives me y equals 1, try again. Superscript, not so. X to the 1 equals x. In other words, if y equals 1, return x. That's a good base case. If I don't have to worry about negative numbers or things like that. I could deal with, if I had to worry about 0, I could deal with if y equals 0, return 1. If I had to deal with negative numbers where we're taking, basically 1 over x to the y, I could write a base case to deal with that. But for now, I'm just going to assume I'm going to get a positive integer for y. So I'm just going to say my base case is if y equals 1, return x. Okay. And my recursive case is simply return x times exponentiation function of x and y minus 1, right? I'm just going to take 1 off of y And if I wanted to go write that code, then that would be fairly easy. I would come down here and say def recursive exponentiation, 2 parameters, x and y. My base case, if y equal 1, return x, else return, I'll put parentheses just to make it clear, x times recursive exponentiation, x and y minus 1. And that is a recursive definition of the function of exponentiation. Okay, I identified my base case, identified my recursive case. Summing everything in a list, okay, just add the numbers up. Again, iteratively, if I wanted to add the numbers in a list, I would just say sum equals 0. Sum for I in range of length, my list L. Sum equals sum plus L sub I. All right, that's my iterative solution to the problem. My recursive solution, my base case is fairly simple. If the list is 1 element long, I'm going to presume it's a real non-empty list. And so if length of list is equal to 1, I'm simply going to return that value, L sub 0. That's my base case. Now, you could equivalently write a base case that said if length of L equals 0, return 0. That works too. You could do that. I'm not going to do it, but it would also work. I want to get back to the recursive case, though. So if there's more than 1 element in the list, then all I'm going to do is return the sum of the list from the beginning, not including the last element. So in other words, to minus 1. Okay, remember in slicing right here that when I had this value right here, this list element right here is not included in the slice. So by just saying start from the beginning and go till, leave out the last element, go to minus 1, that gives me everything except the last element. So I chop the last element off and I return that value. Whoops. And now I have to add plus L sub minus 1, or I'm going to lose that. Now that's doing it with the last element in the list. I could easily do it with the first element and work that way, but that recursive case works as well. Okay. I'm not going to bother writing that code because we're running low on time, but that's an example of how to solve that problem with recursion. So again, why do we use recursion? Because sometimes it makes the problem easier to think about. When do you use recursion? Well, either when you're told to in a class or when you think it makes the problem easier for you to understand. That's when you use recursion. Do you ever have to use recursion other than when you're told to by a professor? No, you never have to use recursion. You can write everything iteratively and it will always work. can always work if you do it right. Sometimes you're making the problem uglier and harder, but that's okay. It will always work. You use recursion because sometimes it makes problems simpler, and we don't care about speed and memory because with cloud computing, that stuff's cheap or free. So we don't worry about that. That's what you need to take away from this class about recursion. Now, you get the lab is about recursion. Next week's homework 6 will be about recursion so that I can prove you understand it. But what you need to take away is base case, recursive case, have to make it simpler, use it when it makes a problem easier to understand. That's all the lecture material I have for tonight. What I'm willing to do now is answer any questions you have about the lab or the project. If you don't have any of those, you're free to go. I will post the recording on YouTube as soon as WebEx makes it available to me in a couple of hours. And I will see you next Monday. I will stop recording because we don't need any questions.